Okay, the final topic that we're going to deal with respect to fluids is fluid drag. So like in the case of something that's moving through air, it'd be air drag, but similar thing for if it's moving through water. And this divides into the two regimes of flow that we've been talking about. So if you're in the laminar flow regime, and again that roughly means that your Reynolds number is less than 100, it behaves one way. If you're in the turbulent flow regime, it behaves another. And so we're going to think about the one case that has been exactly solved, which is a sphere moving through a liquid, or moving through a fluid. Sphere moving in fluid. So you might have a sphere like this that's moving through stationary fluid, but of course that's equivalent to a stationary sphere with fluid moving past it. Those are exactly the same situation, just viewed in two different reference frames. So Stokes showed, and his proof is well beyond the level of our class, that the magnitude of the drag force in this case is 12 pi times the viscosity times the diameter of the sphere times the velocity. So this is the diameter and this is the velocity. So this is usually called Stokes drag, and even when you're not talking about a perfect sphere, it's often used as an approximation, but in many cases you are talking about something that is pretty darn close to a sphere. So then the opposite limit would be turbulent flow. So Reynolds number greater than 10,000. So like, for example, a baseball under most circumstances. And we have the tools that we need to analyze this one ourselves. So let's go ahead and do that. So again, well, I'll draw it as a sphere, but really we could generalize our arguments to any kind of a shape. And this sphere, again, it could be moving to the right relative to the fluid, but it's a little bit easier to think about the fluid moving to the left relative to the sphere. And I want to think about the volume of fluid which is going to impact on that sphere in a time delta t. So fluid that will impact on the sphere in a time delta t. So the fluid is traveling with a speed v. So the part that's going to hit it in a time delta t has a length v times delta t. So all the fluid in this volume, so this is a volume that has a sort of circular cross section, is going to hit the sphere in this area. In this time. So let's say that the cross-sectional area of this tube of air that's going to hit it, which is also equal to the cross-sectional area of the object. The cross-sectional area is A. So A is the area of the object perpendicular to the flow. So, for example, if you had a rectangular solid object like this, and the flow were like this, we'd be interested in the area of this end cap, the area that's perpendicular to the flow. And we are going to make the assume that a fraction equal to C sub d over 2, that's not a two-letter subscript, so let me make it more obvious that that's a subscript, of the momentum in the fluid is transferred to the object. So here's our object. This, maybe it's a sphere or something else. And we've got this volume of fluid that's moving towards it, and we're going to assume that this particular fraction, CD over 2, where CD is a constant, will be transferred to the object. That constant CD, that's called the drag coefficient. So CD is the drag coefficient. And that's how it's defined, through this assumption that 1/2 times CD of the momentum in the fluid is transferred to the object. So if CD equals 1, then half the momentum is transferred to the object. So that we're going to calculate the force that's exerted on the object, the drag force from this fluid flowing past it, F drag. We can calculate that by using what we know about momentum, because we know that the impulse created by that drag force is equal to the associated change in momentum. And so that's sort of what we remember from our definitions of momentum. And so this delta P, that's this fraction, CD over 2 of the momentum in the fluid. So delta P will be equal to CD over 2 times the momentum in the fluid, which is the mass of the fluid, times its velocity. And the mass, so that's CD over 2 times the mass, which is the density times the length of the tube of fluid. So if we just scroll back up a little bit, so this length times the area, that gives you the volume. Length times area gives you volume, multiply that times rho, it gives you mass. So rho times the length, which is V delta T, times the cross-sectional area gives you the mass, and then we have to multiply that times V again. All right. So then we will take this equation, and maybe I'll just rewrite it here. F drag delta T equals CD over 2 rho. We've got two factors of V, so it's V squared A delta T, and we can see that the delta T's cancel out. And so that gives us the equation for the drag coefficient in the turbulent regime. And notice that the drag in the turbulent regime is proportional to V squared, whereas the drag in the Stokes regime, that is laminar flow, is only proportional to V. So that's one of the reasons that the Reynolds number is so important, is to try to figure out which regime are you in, which formula should you use to calculate the drag due to your fluid. Okay, so let me now ask you to work a problem. So I will ask you to calculate. This is going to require you to synthesize a few things we've been talking about recently. Calculate the power needed to drive a small airplane. The power needed from the propeller to drive a small airplane. And so let's give you some numbers. So airplanes are designed to be aerodynamic, to have low drag as much as possible. So a realistic number for the drag coefficient of an airplane might be about 0.03. And again, that's a dimensionless number. The cross-section for a small airplane, we're talking about, just an airplane that can carry maybe a few people. The cross-section might be about 15 square meters. And again, the density of air is 1.2 kilograms per meter cubed. And we're going to assume a velocity of 150 kilometers per hour. And I'll go ahead and do the conversion for you. That's 41.7 meters per second. So I want you now on your own, pause the video now, and try to work this all the way to the end, get a number in watts for the power that's needed to drive this. Okay. So first, maybe let's draw a free body diagram for the plane. So here's the plane with its tail and its propeller here. And so there is a force being applied forward from the engine. And if the plane is moving at constant speed, that will be equal to the drag force, which is acting backwards on it. And the power that's needed is the force times the velocity, as long as we're talking about something where the force and the velocity are in the same direction. And since the force that's needed to drive is equal to the force that's needed, the force created by the drag, we can just plug in our formula for the drag. So the power would be the drag force, so that's CD over 2 times rho v squared A, times this other factor of velocity, times the velocity. And so let's just rewrite this as CD over 2 rho v cubed A. So it's interesting that the power that's needed to drive the airplane forward is proportional to the cube of the speed. And it would be the same thing if you're driving a car, if you're only thinking about the component of power that's needed to counteract the air resistance, it's proportional to the cube of the speed at which you're going. And so back when we had the oil crisis in the 1970s, the national speed limit was lowered from 65 miles an hour to 55 miles an hour. And that might not seem like that big of a change in the speed, but it's a huge change, or a relatively large change in the power requirements, because the power is proportional to the velocity to the third power. Now, of course, you're exerting that power over a longer time. So if you think about the energy that's needed to get someplace, that would only be proportional to v squared. But still, it's a substantial savings. So let's go back and go ahead and plug in the numbers. When I did this, I got about 19.6 kilowatts, which is 26.2 horsepower. Now, of course, the actual engine would have a higher horsepower rating than that, because not all of the energy in the engine is going into driving the plane forward. A lot of it is going into moving the engine parts itself and things like that. But that seems sort of roughly a reasonable number for a small plane. Okay, that's it.